of the real classic geometrical shapes that we see out there as a solid is the pyramid. So I thought it'd be sort of fun to take a look at it. The Egyptians have thought about this over hundreds and thousands of years, and in fact we think about these things today. So here's an example of a pyramid. I just want to sort of talk about a few of these parts. First of all, it's clear that we've got this base, and that base can have a variety of shapes. This one looks like maybe a rectangular base, but you can imagine different types of base. And basically all we have is a base, and then a point on top, a vertex on top, and then we sort of draw lines from the vertices on the base straight up to that top vertex, and that's how we produce a pyramid. Now, there is one particular feature about a pyramid that's a little bit novel, and that's the distance known as the slant height. And the slant height is nothing more than the distance from the very top right along this center face, forming a right angle here. That length there, which is sometimes noted as script L, is known as the slant height. And you'll see that actually coming into a variety of formulas, in fact, right now. So let's take a look at a couple of the objects we can measure here. One thing we can measure is the lateral area. What's the lateral area? Well, you might remember that's just the surface area around. So in this case, it would be the surface area around the pyramid, which means the surface area of everything except for the bottom. And what's the formula for that? Well, it sort of looks like the formula for a triangle, which is not too surprising when you think about that. In fact, each of these faces is a triangle, and so to find the area of that face, we have to have 1/2 base times height. Well, the height is what we're calling the slant height now, and the base is this length right here. But we're going to do that for every single one of the triangles, which means we're going to have this length of that part of the base, this length, and this length. When you add all that up, that's just the perimeter. So we see 1/2 perimeter times slant height. That's just because we have a bunch of triangles, and we're trying to find the area of all the triangles at once. So the lateral area for a regular pyramid actually makes a lot of sense. And the surface area is just the lateral area plus the area of the bottom, the area of the base. So again, not a huge surprise here. Let's take a look at some examples where we can see these formulas coming into play in a beautiful and exciting way. So, first of all, let's consider a regular square pyramid with base edge length 4 inches and slant height of 10. And what I'd like us to do is to find the lateral area and the surface area. Well, it might be sort of fun to sketch a little teeny picture of this, just to sort of have us see what's going on here. So I'll just sketch a little picture. We want a square base. You're saying, why is he drawing them dotted? Well, because once I put this top in, you see, those will actually be hidden. So there's a pyramid. There's my artist's rendition, anyway, of a pyramid. And what I want us to do is I want us to now label what we have here. So a regular square pyramid. So that means that the base is a perfect square, and the edge length is 4. So that means that this is 4 here, but since it's a square, we know that everything is 4 all the way around. And we're given that the slant height, remember that's that new funny length that goes right from the center of one of the edges, right up, straight up, perpendicular to the top. That, and you can see it's sort of a slant. That slant height is going to be given to be 10 inches. And so now let's find the lateral area. So remember, that's just the area around. That's sort of finding the area of 4 triangles. So it's going to be 1/2 the base, which is going to be the perimeter. So that's going to be 4 plus 4 plus 4 plus 4. So that's going to be 4 times 4, which is 16, times the slant height, and the slant height is 10. And so what do we see here? Well, we see 8 times 10, which is 80. And what are our units? Our units, of course, are, well, it's area, surface area, so it's inches squared. That's right. Okay, good. So that's the lateral area. And what about the actual surface area? Well, the surface area is really easy. It's just going to be the lateral area. That's what we just found. And then we have to find the area of the base. Well, the area of the base is just going to be the area of a square, which each side being 4. So that's going to be 4 squared, which is 16. And so that produces an answer of 96, and again, the units are inches squared. So you can see, not a big problem. These make a lot of sense, and you can actually compute various surface areas or lateral areas for the regular pyramid using this formula. Let's try something a little bit more exotic, just a touch more exotic, not crazy exotic, but a little harder. Let's take a look at this regular hexagonal pyramid. Now, why is it called a hexagonal pyramid? Because the base is now a hexagon, and you can see we have 6 sides here. So regular meaning that we have a regular hexagon, and we have this point way up there. And now you're going to see that finding the lateral area is still no problem. Finding the area of the base is going to be a little tricky, since in fact that's something a little bit more exotic than from the square. So let's try to find both the lateral area and the surface area. Okay, so we have a picture in place. Let's find the lateral area. So the lateral area, we know, is just the area of all those triangles. Now we have a bunch of triangles, though, right? What's the perimeter now? I've got 2 on each side because it's a regular hexagon, and I've got 6 of them. So that's going to be actually 2 times 6. And that's the perimeter, and then I have to multiply that by 1/2 the slant height. And the slant height is given by 8. So 8 meters is this length right there. In fact, maybe I should just draw it in so you can see a good picture of it. Right along that face, right in the center here, and straight up, and that slant height is 8. So I multiply by 8. And so what do I see? Well, 8 divided by 2 is 4. 4 times 6 is 24. And 24 times 2 is 48. And what are my units here? These are meters, but this is representing area, so it's meters squared. Okay, so that wasn't the real tough part. The tough part now is going to be to find the surface area, because there, I know it's going to be 48. That's the lateral area, plus the area of the base. Now, finding the area of the base is going to be a little bit tricky. I'll just say one word about that really fast, which is to realize that, in fact, that base is actually made up of a whole bunch of triangles. Just look at the base now. There's the center of the base, and notice that if I were to connect these, I'd actually see 6 triangles. And so I have to find the area of each of those 6 triangles. And so what is the area of each of those 6 triangles? Well, if you take a look at this here, we know that each side is 2. And then what is this perpendicular length right here? Well, you could use a little Pythagorean theorem, because we see that in a regular hexagon, we know that each of the angles in this little triangle is going to be 60. So this is a 60, 60, 60. It's an equilateral triangle, so this is also going to be 2. And so this, therefore, if you use Pythagorean theorem, is going to be the square root of 3. So, given all of that, we can actually find the area of the base. A little bit tricky, and we see it's going to be, in fact, let me just write here as a little side calculation. The base area is going to be, well, I've got 6 of these triangles, so 6 times the area of each of those triangles, which is 1/2 the base, which is 2, times the height, which is the square root of 3. And so now I see the 2 and the 1/2 actually can simplify down to just 6 square root of 3. And so that represents the area of the base, and so if I add that in here, 6 square root of 3, then that sum represents the total surface area, and again, the units are meters squared. So there's the answer for the total surface area. Here is the answer for the lateral area, and you can see how these formulas really allow us to uncover the structure of what's going on with regular pyramids.